So guys, this podcast is a very quick overview of basic equilibrium. An equilibrium is a situation where you have two reactions that are competing at the same time, and they take place in a special situation. First of all, the container has to be closed. Okay? And so equilibrium actually happens in your body all the time. You just don't really know that or really put it to use because you don't think of yourself as a closed container. But if I have a container that's got a cork in it, and I've got a reaction going on inside, okay, and there's a bunch of gases in here, I could put N2 gas, we're looking at this above equation in this box right here, and H2 gas, and it would react in this ratio, and the forward reaction, N2 and H2, would produce NH3 in this ratio, always, okay? So if I put these two ingredients in here, N2 and H2, this is the reaction it would follow. All right? Now, since this container is closed, I could also put ammonia in here, just NH3. And the NH3, by putting NH3 in here, it would actually break down and it would form H2 and N2 in the form of a gas. So this is called equilibrium. When you have two competing reactions, a forward reaction and a reverse reaction, and by the way, these would all be in a mixture, and they'd always be in this relationship. They'd always have 3 of these, moles of those, H2 hydrogen gas, to 1 mole of nitrogen, to 2 moles of ammonia. And so instead of writing two separate equations like this, we put a double arrow, and it's called an equilibrium reaction. And what's true in equilibrium is that there's a forward reaction and a reverse reaction, and they happen at competing times. So the forward reaction is what? The N2 and the H2 bumping into each other, and these are both gases, and they form NH3. This happens at a certain rate. At the same time, the ammonia as its form is breaking down, okay? And as the ammonia breaks down, it forms hydrogen gas and nitrogen gas. So there's a forward reaction and there's a reverse reaction. And the key thing about equilibrium is that the amounts are not equal. The key thing is that the rates are the same. The forward and the reverse reaction are the same. Now there's something called the law of mass action. And this is so that we can actually do some calculations and figure out how many products or reactants are around or what the ratio is for a certain reaction at a certain temperature. And to write the law of mass action, you simply write the letter K, okay, and I like to misspell equilibrium and misspell it with a capital K in it. I know it's not proper, I don't really care, okay? It helps me remember that equilibrium is represented with a capital K. Now, what does capital K stand for? It's a ratio of your products to your reactants. Now, what do we know about products and reactants? Always. Okay? The reactants are always what you start with. They're your ingredients. And so these are your reactants. You know what I'm going to do? I'm actually going to do these in different colors so that you can look what's going on here. So I'll do this and I actually should just write this like this. I will make the products so they're blue. Oops. I'll make the products so they're blue. And the reactants so they're red. Okay? All right, now let's get this set up. So what are my products? My products, I only have one of, is NH3. I take the NH3 and I put it in brackets by convention. This is how you do it. And the 2 that's up front, that coefficient, becomes an exponent. Okay? That's how you write it. You start with your products, and now you're going to use this line right here as a line in your fraction. So this double arrow in your reaction becomes a line mathematically. Now, These are my products, or my only product in this case. Where are my reactants? These are my reactants, my ingredients. And to write them properly, there's two of them. It doesn't matter which order I put it in. I'm going to go ahead and use hydrogen because I'm done with this, and now I'm moving in this direction, and I'm going to find this first in my steps. So I have H2. What's out front? Oh, there's a 3 out front, so I'm going to put that 3 up top. All right? And this plus is not a plus sign when it comes to doing the math. You multiply them. Okay? And I put N2 here. And it's to the first power because there's a 1 out front. You don't need to write that if you don't want to. All right? So what have we done? We have written our products over our reactants. All right? And we'll come back to what the states of matter are in a second. But do you see how that worked? Let's review that one more time. Here's my NH3 in blue, and I put it on top, NH3, and I went ahead and took this coefficient up front and put it up here as an exponent. What happened next? My double arrows right here became my line in my fraction. And then I moved on to my next component, which is a reactant. And I put my H2 here, didn't I? And that 3 out front becomes my exponent here. My N2 is my next component, my reactant. I do not put a plus sign, do not make that mistake. And there's a 1 out front, and so that 1 becomes my exponent. Now, there's no math at all right now, is there? There's just, can you write the equilibrium expression? So this is called an equilibrium expression. It is the directions that I use just in case I have math to do. Okay? So before we move on, let's practice writing some equilibrium expressions. Now, I will tell you right now that when you write an equilibrium expression, which is a K value, capital K, which is the products over the reactants, okay? I do not include solids, and I do not include liquids. I do include aqueous, and I do include gas. So no solids and no liquids. Okay? None of those. So let's see what you run into in example A. I have all gases, don't I? Gas, gas, gas. I'm going to take my products, okay, and I'm going to write it down here for you. So A goes here. I'm going to take my products, and if you want to write P over R, you can. And my product is SO3. I put it in brackets, that implies concentration. And I put the 2, that's the coefficient, up top as an exponent. There's my line for my fraction right here. See that right there? That turns into a fraction line. And then I run into O2. And if I write to the first power I can, or I can just leave it blank up here. I can write 1 or not. Remember that plus sign becomes a multiplication sign. And I write SO2, and I put that to the second power because I have the 2 up front. Make sense? Okay, now let's look at example B. What do I have got going on in example B? In example B, I have a solid. Uh-oh, you don't write it. I have a solid. Uh-oh, you don't write it. So for B, what do we have? My equilibrium expression, my law of mass action expression, is written as products over reactants. Well, guess what? I don't have any reactants, do I? I do have one product, however, that's a gas, and that is CO2. What's the coefficient that's out front? Oh, it's a 1. So I go ahead and either write it to the first power or leave it blank. See that? Now, what if this was the case? What if it was written in the reverse direction? What if I had this as my problem? I'm going to go ahead and flip it, okay? What if I started with carbon dioxide, gas, okay? And that made CaO solid. Oh, excuse me. And I put it with CaO solid. And that made calcium carbonate. How would I write this? Well, what would you do? If you notice, the carbon dioxide is now a reactant. I didn't trick you. I'm not trying to trick you. I'm just saying, what if it was written in this format? Well, what do we not include? We do not include solids or liquids. Are there any solids? There sure are. There's a solid here, right? And there's a solid here. Cross them off. What is this? This is a reactant. So what do I do if I write an equilibrium expression? K equals products over reactants. And therefore, I'm going to put a 1 here because this is a constant, right? This is just 1. It's one thing that's there. I don't include this at all. I could put a 1 there if I wanted to. That's why it's a constant. That's why I cross it off. And then I put CO2 here, and the exponent here in this case is 1. So I don't have to include those 1s, at least this one, correct? But I do need a 1 up top because it needs to have something in the top. And that's how you do that. So no solids or liquids, guys. Now, this is a graph, and these brackets over here stand for concentration. So let's just call this concentration of A, okay? And to do that, I'm going to go ahead and just look at the blue line, concentration of A, okay? Because this is really concentration of everything, of my products and my reactants. So in reality, isn't this true also? What's this graph show? It shows a purple line and a blue line, okay? Now, my reactants in this case happen to be blue. How do I know that? Well, if this is time 0, and this is time lots of times gone by, what's true at time 0? I have something of the blue line, don't I? What do I have at purple? I have nothing. That means my reactants, don't I start with reactants? Right? They should be in blue. I start with my reactants. What's true about them? They react. What happens to the amount? They decrease. Why? What are they doing? Oh, they're reacting. And so look what happens to them over time. They are decreasing, aren't they? But eventually they level out, and that's what equilibrium means. Okay? They reach an equilibrium. They balance out. Now what happens to the purple? Well, what is the purple? The purple are my products. And how do I know that? Well, at time 0, what do I have? I have nothing. See that right there? But what's happening to it? Oh, it's increasing. And that's what happens. As products are formed, they increase. And what happens to them? Well, they don't continue going through the roof. They balance off. And what is true in this area of the graph? It's reached equilibrium. See that? Okay. Well, let's learn how to use this. This problem says find K, or find the value of K, or find the value of the equilibrium constant. Well, what do we have to do? Here's my problem. I look at it and I say K. Oh, that's equilibrium. That's what Faley told me. Faley told me this was equilibrium, right, with a capital K. So what is that? Oh, that's products over reactants. And she always told me not to include solids and liquids. Are there any solids or liquids here? No, they're all gases. How do you write a value of an equilibrium expression? Well, you go ahead and put products over reactants. So I'm going to go ahead and write NO squared, make it equal to K. Okay, and there's my line, right? There's my line right here, my line and my fraction. I'm going to write O2 and N2. Okay? Now if you look at that, what is true here? Let me find the problem I'm doing so I can actually go through this without doing the math as quickly for you. Sorry. So what has to happen in this case is I needed to write my directions first. I needed to write them properly, didn't I? Okay? So if you look at this, sorry, just looking for the answer real quick so I don't have to take time on the calculator and take away from what we're doing. So these are my actual products over reactants. Before, back here, we just wrote these equilibrium expressions, didn't we? Right? There were no numbers. I wasn't asking you to find a value. But this says find K, which actually means find the value of K. And you know that because they give you numbers. So I'm going to go ahead and take these actual numbers and plug them in. So if you look, where's NO? Well, here's NO right here. That goes up top. So 4.7 times 10 to the minus fourth. And what do I do with it? Oh, look, it tells me to square it. Do you see what I'm doing here? I'm taking these numbers and plugging them into my directions. Then I'm going to go ahead and find the value for O2, which is 0.00. Be real careful with these. I always make mistakes and put one too few or one too many zeros. And that's going to be the first power, isn't it? That's why I like writing it the first power. Just because it makes me comforted to know what I'm doing properly or not. And what I put here, 0.041 to the first power. So what have we done? We've written our directions. We've plugged our numbers in. Why do we plug numbers in? Oh, because they gave them to us, okay? And if you solve, you get 3.2. Excuse me, you get 6.9. Probably going, what are you doing? You get 6.9 times 10 to the negative fourth. Now, there's no value of units for these. No units. There actually are units, but if you look at the equilibrium expression for this example, and the equilibrium expression for this example, and the equilibrium expression for this example. They're all different. So you'd actually have different units, which makes no sense in the world. So this is just a ratio. What's it a ratio of? Oh, that's right, products to reactants. And so this is how you solve. Let's try a different one. Okay? So this says find Kp. What the heck is Kp? Well, it turns out that this right here can be called Kc because we're talking about concentration in terms of molarity. I can also call it K, or in some old books you'll see it called Keq, the equilibrium constant. Yikes. Okay. So what's the difference? Well, this is called Kp because it's in terms of atmospheres. Concentration, Kc, is in terms of molarity. See that? Molarity. Kp is in terms of atmospheres. So how do I find Kp? Well, what's K? It's a ratio of my products to my reactants. Okay, I'm going to go ahead and I'm going to write my equilibrium expression. K equals NH3. How do I write it, guys? I take that 2 out in front and put it up top here. There's my fraction line, right? Okay, and then I'm going to go ahead and draw my line. I'm going to put my H2 here, and 3 here, and N2 to the first power. Big question I get asked is, can you write it like this? Is there a difference? Like here's my products and here's my reactants. And I would tell you no. It doesn't matter, does it? There's no order to how you do things, at least when you write them on there. If I asked you to make me a jelly and peanut butter sandwich, you go, well, okay, but I'd still have peanut butter and jelly, wouldn't I? So if you notice what's true about the order of these two, they don't matter. Just like I could say this is 3H2 here, plus N2 makes 2NH3, right? It doesn't matter. It doesn't matter the order of what you put things in, okay? I just like doing this, and I go backwards because this whole thing is backwards from what I know. I start with my products and end up with my reactants. Right now, what do you do? Well, what we do before. If we had values, you plug them in. So I find my value for the pressure, that's what this stands for, the pressure of nitrogen gas, or excuse me, pressure of ammonia gas, sorry, is 3.1 times 10 to the minus 2, okay? Now, in this case, because I'm using gases, a lot of times you'll see things in parentheses. That's how you know that you have things in terms of atmospheres. So really, truly, what I should have done up top here is I should have put these in parentheses, okay? Those parentheses tells me that my values are in terms of atmospheres. Brackets means molarity. And again, if you do that, I'll give you extra credit. All right, now, what do I know at the bottom? I know that my pressure of hydrogen is 3.1 times 10 to the minus 3. And what do my directions tell me to do? Cube it. And here is 8.5 times 10 to the minus 1. And put it in brackets. Why again? Oh, because it's in atmospheres. Now if I actually solve this and plug things in and do my math, I get, make sure I'm doing the right one here, I get 3.8 times 10 to the fourth. That's my answer. So my value is 3.8 times 10 to the 4th. Now, why is that? That's because when I solve my math right here and follow my directions using the values they've given me and plugging them in, that's what I get. That's my value for K, and it's Kp in this instance. Okay? Now, for those of you in AP who are interested for honors credit, find Kp if K is equal to 3.7 times 10 to the 9th. Well, this is like saying, I want to know things in terms of molarity, and this is in terms of atmospheres. So right now, if you measured this person, if you measured their height in inches, right, you got a ruler and you measured their height in inches, and you measured their height in the metric system in meters, right, in feet, or in meters, right, centimeters, guess what? Their height wouldn't change. Their height would still be the same, but the numbers would be different. Why are the numbers different? Because this is in terms of inches or feet, and this is in terms of centimeters or meters. So the measuring system you're using is different. And so that's all this is. This is a conversion factor to go back and forth between Kp. What's Kp? This is in terms of gases as in atmospheres, right? And this is in terms of molarity. So now you have your way to go back and forth between two different terms, and it's a conversion factor. And this is how you do it. So, how would you do this problem? Well, you would think you'd have to write an equilibrium expression, but you do not. Okay? And so what you need to do is, you know what K is. You know what this is right here. What is it? 3.7 times 10 to the 9th. How do you know that? They give it to you, don't they? That's in terms of molarity. Now, what's R? R is in terms of gas laws. That's 0.0821. Okay? Now, they would have to give you a temperature. Okay? And so I'm going to tell you that this should have said at 25 degrees Celsius. So if it's at 25 degrees Celsius, what do you have to do if you're doing things in terms of gas laws? I'm going to go ahead and add 273 to it. And so that's 298. So this is times 298. Okay? So what's true? This delta N means in terms of moles. And what's important about that is there's a mole here and a mole here. And there's also a mole here. So this delta N is products minus reactants. How many products do you have? You have one. Right? Don't you have one right here? How many reactants do you have? 1 mole and 1 mole. What's that? That's 2. So 1 minus 2 is minus 1, isn't it? So this whole value right here is going to be to the negative 1. So to solve for Kp, I needed to do what? Write my value for K, which they gave to me. Write my value for R, right? Here's my value for K. They gave this to me right here. And again, I always do that. I always choose the eraser. Okay, or forget I'm on the eraser. That's my value for K. They gave it to me. This is my value for R. It's my gas laws R. This is my temperature, 298 plus 25 degrees Celsius. And how did I get this negative 1 again? I took this 1 and subtracted these 2 from it. Okay? So, now what do? Now I solve. Let me get rid of this junk here. Okay? And all I'm doing is using this equation to help me solve. And when I do that, I get 1.5 times 10 to the 8th. And that's my value for Kp. And the minute I see Kp, folks, what's that mean? That's in terms of atmospheres. Okay? All right, we're going to stop here.